So today's topic is energy conservation and transformations. So we already know all of the equations and theorems and theories that are going to allow us to develop today's topic, but today I wanted to take it to a higher level and be able to solve more complex problems and that are more common in real life. So the first thing that we need to remember for today is the law of conservation of energy, which is that energy cannot be created or destroyed, only transformed. So 2 classes ago, we had written that as an equation because we had defined mechanical energy as the sum of potential and kinetic energy. So it was potential energy plus kinetic energy, and that includes all types of potential and all kinds of kinetic energy. And mechanical energy, we had said, is conserved when there's no friction. So this is conserved with no friction. So we can write that, now that we know the types of potential and kinetic energy that exist in their equations, we can write this as a bigger equation. So we learned about 2 potential energy equations last class, which were gravitational potential energy, GPE, and its equation was m times g times h. We also learned about EPE, elastic potential energy, and its equation was 1/2 kx squared. And we learned about kinetic energy and its equation, which was 1/2 mv squared. So these are the 3 equations that we have. And we're saying that mechanical energy is conserved when there's no friction. So if we want to do this for the case in which there is no friction, we can write it as an equation in the following way. So suppose we have a situation 1 and a situation 2. In the situation 1 and the situation 2, there's going to be the same mechanical energy because mechanical energy is conserved. So we start with the situation 1. Suppose a ball is being held above the ground by a hand. And the ball has some potential energy. That is situation 1. And then the ball is going to be dropped, it's going to fall down to the ground, and that's our situation 2. So when we're talking about situation 1 and 2, it's a situation that happens one before and another after, but in the same system. We're talking about the same system. So the situation 1 is going to have a mechanical energy given by its GPE, EPE, and KE. So we're going to have GPE 1, which means the gravitational potential energy of situation 1. We're also going to have some EPE in situation 1, maybe, in this case we don't, but in general, and some KE of situation 1. And when we get to situation 2, we're going to have our GPE2 plus our EPE2 plus our KE2. And since the total mechanical energy, all of the potential energies and the kinetic energy are conserved or constant, then these 2 are going to be equal. So this is what our equation looks like. And we can put these formulas inside of the equation, if we wanted to plug the values in. But it's not necessary. You can just, we can leave it like that so that you guys know. So this is our first equation, and it's for when there's no friction. And we're going to do an example of this in a second. So what we're going to have in specific examples is that there is not always GPE and EP and KE in each of the before and after situations. So some of these things will cancel out. So our equations will never have these 6 terms. They will maybe have 1 on this side and 1 on this side, or 2 on this side and 1 on that side. Any combination, but it's very uncommon to find an example where there's all of the terms. So you just have to choose what's not 0 to make your equation. So for example, if we were going to use this equation to determine the energies in this example of dropping the ball, well, at the beginning, we would only have gravitational potential energy. So we have GPE1. But do we have elastic potential energy? Is there a spring here? No, so we don't have any of this. Is the ball moving at the beginning? No, the guy is grabbing the ball with his hand, so it's not moving, so we don't have kinetic energy either. So that's it for the left side of the equation. So that's going to be equal to everything that we have at the end. Is there any GPE? Well, now the ball is on the ground, so there's no GPE anymore. Is there EPE? Again, there is no spring, so there can't be any elastic potential energy. But the ball is moving right before it hits the ground. So we do have some kinetic energy at the end. And that's the only term that survives. So basically, the equation that we need to solve for this example is GPE1 equals KE2. And that is going to give us the values that we want. So let's do this example numerically. You grab a ball of mass 2 kilograms at a height of 1 meter. What will be its speed right before it hits the ground? Last year we learned how to solve this problem with the equations of motion, and it was a very complicated process in which we had to put distances, heights, times, accelerations, and many other things. But now we can do it just with this equation. So basically, if we put these equations into here, we're going to get, for GPE1, it's going to be mass times g times height equals, and the KE is going to be 1/2 times mass times velocity squared. And that's the equation we need to solve. We're looking for its speed right before it hits the ground. And all of the gravitational potential energy that it started with at moment 1 is going to be converted into kinetic energy at moment 2. So if we solve this equation for V, we're going to get the answer to this problem without having to use any of the complicated equations of motion. So we put here a mass of 2 times 9.8 times 1 equals 1/2 times a mass of 2 times V squared. We calculate everything. This is 2 times 1 times 9.8 gives us 19.6 joules, which will be converted into, and this is 2 over 2 is 1, V squared. So our speed is going to be the square root of 19.6. So you put it in the calculator, square root of 19.6, and it gives me 4.4. So the speed of the ball when it hits the ground is 4.4 meters per second. And that was the whole process. That's the only thing we need to do. So that is the usefulness of energy conservation. Now, what happens when there is friction? So I'm going to erase this example, and I'm going to do the equation for when there is friction. So you might remember from a couple of classes ago that we saw with the skate park that you guys constructed that some of the energy when there's friction is lost as heat, as thermal energy. So if there is a ramp with friction, the skater lost some of its energy and eventually he stopped. So this will not be true in that case because some of the energy will be lost. So we need to put another term inside that gives us the energy that's left. So we start in the same way. The guy, the skater, let's say, has an initial GPE, an initial EPE, and an initial KE. And at the end, he will also have a GPE, an EPE, and a KE. But in this case, since there's friction, there's going to be less of this mechanical energy at the end than at the beginning. So we need to subtract something from the energy at the beginning so that we get the true energy at the end. So what is it that we need to subtract? Well, we need to subtract the energy that was lost because of friction. And what is that? Well, energy was lost because the force of friction did work. So basically, the term here that we need to subtract is the work due to friction. So a reminder for you guys, work was force times distance. And friction force is our friction coefficient mu times normal force. So we can put this inside our equation for work and get the following. Work due to friction is equal to this force, mu times normal force, times x. So the work due to friction is going to be equal to the coefficient of friction, the coefficient of kinetic friction because it's moving, times the normal force of the object, times the distance that it travels through. So this is going to be our big equation when there is friction. This is the one that we're going to use when there is friction. And this is going to give us that the energy at the end is less than the energy at the beginning because some of it was lost. How much of it? Mu times normal force times the distance that it traveled. So using this, we're going to do a second example. I'm going to put this up here. So the work due to friction is mu times normal force times distance, so that I can erase this here and do the example on the bottom. So this is an example with friction. Let's say there's a ramp, an inclined plane, like we saw about 3 classes ago. And we have an object at the top, and it's at a height of 2 meters. But it's going to cover a distance going down the ramp of, let's say, 3 meters. Of course, it's longer. The hypotenuse is longer than this angle. So we want to see how much speed the block has when it reaches the bottom of the inclined plane, taking into account the fact that there is friction along this ramp. And the coefficient of friction is 0.1. So what is the block speed? So the question would be, let's say we have a block of mass m equals 1 kilogram. What is its speed at the bottom of the ramp? You remember the ramp has friction. So we use the same equation. The block is initially at rest at the top of the ramp. So what do we have to use? So now we're using the second equation. Do we have any gravitational potential energy? Yes, of course. So we have GPE1. Do we have elastic? No, there is no spring. Do we have kinetic? No, the block is at rest. Do we have work due to friction? Yes. So we have to subtract the work due to friction. We'll put in the numbers when we get our equation. And that's it. Equals. At the bottom, does it have any gravitational potential energy? Not anymore, because it's at the bottom. Does it have elastic potential energy? No, because there's no spring. Does it have kinetic energy? Yes, because it's moving at a certain speed. So we do have a KE2. So basically our equation is similar to this one, with the exception that there is some work that friction is going to do that is going to waste some of its energy. So we have mass times gravity times height according to our equation. So that is 1 times 9.8 times our height is 2. Remember, we're talking about the height, not about the distance down the ramp. Now we're going to subtract W. That is mu, which is 0.1, times normal force. I'll give you the normal force because if you remember, the normal force in an inclined plane depended on cosine of the angle, and I haven't even given you the angle, so I'm just going to tell you right now the normal force is 7.3. Okay, so mu times normal force times the distance. In the distance it covers is not 2, it's 3 meters. So 2.3 times 3. And that's going to be equal to 1/2 times the mass of 1 times v squared. So we solve everything on this side, which is going to give us, so this is 21.9, 2.19, and this is 19.6. So this is going to give us 1917.41. And this is 1/2 times 1 is 0.5 v squared. So if we pass this to divide, we're going to get that v squared is 17.41 over 0.5. And if we take the square root, we're going to get v. So let me put that in my calculator. Square root of 17.41 over 0.5 gives me 5.9. So v is 5.9 meters per second. So we got the speed of the block at the bottom, and we didn't have to use acceleration or our equations of motion or anything that complicated. We just needed to plug all the values into our equation, depending on what there was at the beginning and at the end. So that is basically how to use the equation with friction and without friction. And you're going to get a lot of examples in the activities that you're going to do now. Sometimes there is GP at the beginning, sometimes there's EPE, and at the end sometimes there's KE or GPE or something else. And you just need to figure out what to use, which equation to use depending on if there's friction or not, and which of the three terms, 1, 2, or 3 terms, you're going to use for the beginning situation and for the end situation.